Amardeep Sarkar, who is a postdoctoral fellow at the Harishchandra Research Institute, Prayagraj. And today he's going to talk on some aspects of the characteristic metrics. So over to you, Dr. Sarkar.
Thank you. First, I'd like to thank the organizer for giving me an opportunity to talk here. Today, I'm going to talk about characteristic metrics. Most of the person, let me tell that today I'm going to talk a little bit different than I initially thought of giving. So I will talk about characteristic metrics, and most of the part of this talk has been done during my PhD. And so let's begin. Let's. I will outline the first. I will outline the what are the things I'm going to talk today. First, I will define what are conformal metrics. Actually, these conformal metrics arise in geometric function theory a lot, and many often these conformal metrics is studied through external problems in complex analysis. So initially, I will define that these conformal metrics. Then I will talk about the scaling principle, which has been used to prove the theorems I am going to present. And then I'll give a connection between the Alford map characteristic metric and zero kernel and the Gaussian kernels. Then I'll talk about the boundary behavior of this characteristic metric. And then I'll talk about their curvatures and higher order curvatures. And then I'll talk about the submultiplicativity property of the characteristic metric. Let's begin with the definition of conformal metrics. On domains in the complex plane, the characteristic metrics, a general metric is denoted by this tau d z mod dz. Here tau d denotes the density of this metric, and it is just a positive valued function on the domain, on the given domain D. We say this collection of metrics is conformal metrics if it satisfies the pullback property. That is, if you have a biholomorphic map from a domain D1 to another domain D2, so when you pull back the metric tau D2 with respect to the map F, that should be same equal to the metric tau D1. That is, we want this property to hold to be a collection of metrics to be conformal metrics. And the pullback formula is given by this formula, tau d2 of f of z into modulus of f prime of z for all z in D1. Some examples of conform metrics are the hyperbolic metrics. Hyperbolic metric once as example, and at any point z on a domain D it is defined to be the infimum of 1 by f prime of 0, where f varies over all holomorphic functions from the unit disk into the domain D, such that the 0 maps to z. Another example of conformal metrics are the characteristic metrics, which I'm going to talk about today. And at any point of a domain, it is defined to be the supremum of the quantity f prime modulus f prime of z, where it varies over all holomorphic functions from the domain D into the unit disk, such that z maps to 0. If you see the unit disk, the hyperbolic metric and the characteristic metric are same, and it is given by 1 by 1 minus mod z square, and it is the pointer metric of the disk. And in general, they are not same. If you take the punctured disk, they will be different. Now let me briefly say about the scaling principle. This scaling principle has been used in higher dimension to solve several kind of problems. And let me for that we take a domain D in the complex plane and a C2 smooth boundary point of that domain, call it P, and then we'll have a defining function psi near in a neighborhood of the point. We're calling it U, and any point in U intersection G is written as all points where psi is negative, and U intersection the boundary is where it is 0, and we also want that the gradient of this defining function to be non-zero on U intersection D. Now the scaling principle comes. For that, we take a sequence of points in the domain which converges to the boundary point P, and using the defining function psi and this sequence, we define this sequence of affine maps z minus pj divided by minus of psi of pj, as psi is the defining function. Now, if you see the image of the domain D with respect to the affine maps pj, it will give a sequence of domains. We are going to call this scale domains, and we can show that these scale domains obtained in such a way converges to the Hopf space in the Hausdorff sense. I'm not going to say what do I mean by the Hausdorff sense here, but let's note that this sequence of domains will converge to the Hopf space in the Hausdorff sense. So this is going to help us transform the problem of the boundary into an interior problem. Let's see how. Here, Hopf space is defined as real part of omega bar z minus 1 is 0, where omega is nothing but just the gradient of the defining function at the boundary point P. So now we want to transform the boundary problem into an interior problem. If you see, if you take any conform metrics, then we say that we already have this sequence of affine maps. Now what we do, we pull back it is pushed forward here with respect to pj, and with respect to pj inverse it will be pulled back. When you pull back this tau d, the conformal matrix tau d, with respect to this pj, you will get another by the pullback formula this matrix. When you substitute z equal to 0, we notice that these scale domains will always contain the point 0, because at the point pj it is 0. So when you substitute 0, and these are metrics on the scale domains, when you substitute 0 here, on the right hand side we get tau d of pj into minus of psi of pj. This is a boundary problem, as we see that j tends to infinity. And here this is not a boundary problem because the point inside is fixed, but the domain is changing. So thus we have converted the boundary problem into an interior problem, but at the cost of varying the domains. But we already have seen these domains actually converges in the Hausdorff sense, and we are going to make use of that fact. Now let's connect what the Curvature metric and the Alfors map. If you recall the definition of the Curvature metric, it is just supremum of the quantity mod f prime of a at the where f is varies over all holomorphic function in this collection, and we want f of a equal to 0. Actually, we can ask the question: does there exist a holomorphic function which attains this extremum? Actually, there is a holomorphic function whose derivative at the point a is positive, and that function is called the Alfors map. If you have now, let's see how Alfors map can be written in forms of in the form of ratio of 2 kernels. And if you have a bounded domain which is infinity smooth, then the Alfors map at any point A in the domain can be written as just ratio of these two quantities. The SD z comma A is called the zero kernel, and LD z comma A called the Gaussian kernel at the point A. And how how this zero kernel and Gaussian kernels are obtained, I'm not going to talk about that, but I'll just say that these zero kernels are the reproducing kernels which comes from the reproducing kernel Hilbert space known as the Hardy space, and the Gaussian kernel obtained as a conjugate kernel of this zero kernel. Let's talk about some properties of these kernels, and we see that the zero kernel is holomorphic in the first variable and anti-holomorphic in the second variable. And if we fix A, the Gaussian kernel is holomorphic in D minus A, and it has a simple pole at the point A. and we see that the zero kernels are Hermitian symmetric. Using the Hermitian symmetric property, we can easily see that it is greater than or equal to 0 along the diagonal, and hence we can also show that the zero kernel is a real analytic function for any domain which is infinitesimally bounded. Now, the remarkable thing is this, that the curvature metric can be written as 2 pi of the zero kernel along the diagonal, and this will say that the curvature metric is a real analytic function. Hence, we can define the curvature of the curvature metric as well. Now, let's give you the formula for the zero kernel of the half space, where because we are going to use this, and zero kernel, gradient kernel, and the Alford map. The Alford map of the half space is given by this formula. A mod of omega is this same omega to define this half space, and the zero kernel is defined by this formula, and the gradient kernel by this. If you take the ratio of these two, you will get the Alford map, as you can easily see here. And along the diagonal, the zero kernel is strictly positive, as you can see here. Because real part of omega bar z minus 1 is strictly less than 0, so this should be strictly positive. And this is we also mod omega is always positive because it is the gradient of the defining function, as we have seen before. Now let's come to the first theorem of this talk. We're going to prove this theorem in the following setup, where D is a bounded domain with a smooth boundary, and we want P a boundary point psi with a local defining function as before, and we also define the collection of defined maps by Tj with the same formula we did before. And as we know that this Dj converges the half space in the house of sense. So in this setup, we have the following theorem. We showed that the sequence of Alford's map of the scale domain Dj converges at the point A converges to the Alford's map of the half space uniformly on complex subsets of the half space H. Also, we have the sequence of zero kernels of the half space of the scale domains converges to the zero kernel of the half space uniformly on complex subset of H cross H. And we also have this convergence of the gradient kernel on complex subsets of H minus the point A. Now, using the theorem, using this theorem, we can also prove this following theorem, which says that for a bounded domain and for a point in the boundary which is C2 smooth, and hence we are taking a defining function psi of near that point. In that case, in this setup, the theorem says that if you take the product of the Curvature metric and negative of the defining function psi, this limit will go to the Curvature metric of the half space at the point 0, which is mod omega by 2, as the point z goes to the boundary point P. So hence, if you take in place of this defining function psi, if we take the special kind of defining function, we'll get this theorem, which says that in the same setup we have this theorem that says that the Curvature metric can be compared to the quasi-hyperbolic metric of the domain D. This quasi-hyperbolic metric is 1 by distance between Z and the boundary of the domain D. And near the point there, we can compare these two metrics, and actually explicitly we can compute the ratio of these two metrics as the point Z goes to the boundary point P. Next, I want to talk about the Gaussian curvature of the Curvature metric, and the Gaussian curvature of the Curvature metric is defined to be minus of Laplacian of log of the Curvature metric divided by square of the Curvature metric. And if you expand this formula, you will get this expression here, actually this would be a negative one, negative in place of positive. We'll get this formula, and in this formula, if in these terms, if you see here the partial derivative of the Cartesian metric, which is written here, CDij bar is the derivative of the Cartesian metric, I plus j derivative of the Cartesian metric with z and z bar.
Dr. Sarkar, you have 5 minutes left. Okay.
Yeah. So now this theorem says that if you take the sequence of scale domain, then this Cartesian metric of the scale domain will converge to the Cartesian metric of the half space uniformly and complex subset of the half space. And also we can prove this, the curvature of the Cartesian metric of the scale domains converges to the Cartesian metric of the half space, the curvature of the Cartesian metric of the half space, which is equal to -4. And hence, since the curvature of the Cartesian metric is conformal invariant, we get this for a convergence of the curvature of the Cartesian metric of the domain D. Now let's define higher order curvature of the Cartesian metric, and it is defined to be this quantity J7 dz divided by Cz of n plus 1 whole square, and here J and D is determinant of this quantity, and this is the derivative of the Cartesian metric. It turns out that this higher order curvatures are conformal invariant, and these are useful quantities. And when you put n equal to 1, it is the standard Gaussian curvature. And Berger showed that for any domain, the curvature is bounded, higher order curvature is bounded above by this quantity, and equality holds if and only if this is the domain is simply connected. Now we have the following theorem, which says that the curvature of the higher order curvature of the Cartesian metric of the scale domains converges to this quantity. Using this, we have this following theorem, which says that we can compute the higher order curvature of the Cartesian metric of a domain. Means we can say about the convergence of the higher order curvature of the Cartesian metric, and that will exactly converge to this quantity as z goes to the point P for any bounded domain, such that we have the point P to be a C2 boundary point. This is the last theorem of this talk I'm going to talk about. This connects the Cartesian metric of any two domains such that the intersection is not empty, and we want the domains to be smoothly bounded. And this says the following: the Cartesian metric of the intersection of these two domains product with the Cartesian metric of the union of these D1 and D2 is less than equal to some constant into Cartesian metric of D1 and the Cartesian metric of D2 for every point in the intersection D1 intersection D2. And this constant is obtained, which will depend on the domain D1 and D2, and this constant will depend on bounds on the curvature of the Cartesian metric. So thank you. I'll stop it.
Thank you, Dr. Sarkar. And we have about 6 minutes left before the next talk. So if people want to ask some question, please go ahead. If somebody has a question, please unmute yourself and you may ask.
Hi, Amar. This is Gautam.
Yes, hi, sir.
So I have a slightly naive question. During your talk, you mentioned an asymptotic comparison to the pseudo-hyperbolic metric. And you sort of gave a very quick definition and expression, which you call the pseudo-hyperbolic metric. This is the
quasi-hyperbolic.
Yeah. So this is this particular expression. Is it under the assumption that one is at an interior point which is close to a C2 smooth boundary point?
to define the quasi-hyperbolic metric, we don't need this C2 smoothness,
Okay.
and you can define for any domain.
Okay.
But to hold this condition, that means the Curvature metric can be compared with this quasi-hyperbolic
Okay.
metric.
I see.
In this scenario, to explicitly compute this limiting case,
Okay.
we want this to be C2 smooth, and in that case, we can use this function, distance between z and boundary of z, to define the defining function of the domain.
Okay.
And we can use this formula to obtain this.
Yeah. And you can guess why I asked this question, because minus the definition, it somehow looks like it is very dependent on Euclidean coordinates, whereas being conformal, it shouldn't.
Yes,
but what you are basically doing is just stating the result in the above context. Yes.
Yes, right.
All right. Okay. I now understand. All right. Thank you.
Thanks.
Any more questions or comments? So it seems we don't have anybody else. So thank you, Dr. Sarkar, again.